Hi MAH00881 students. It's the weekend and I know that I was going to give you a cliffhanger about isomorphic graphs, but you're all waiting so long you probably want to know the answers to this stuff now. So I decided to make a little video to help you with isomorphisms. This is material that will be covered not on the homework that you're turning in for October 27th, but it will be on the next assignment that will be due the next Monday, which is November 3rd. Basically the idea is if I give you a couple of graphs, we'd like to be able to decide whether they are isomorphic or not. Remember that an isomorphism just means that there's a bijection, a one-to-one onto function between the vertices of the first graph and the vertices of the second graph in such a way that all edges and non-edges are preserved by that isomorphism. So it's a bijection that respects edges, essentially. So for one thing, the graphs that you're looking at have to have the same number of vertices, otherwise you can't have a bijection at all. Okay, but as I discussed in class last week, there are a lot of other things that two graphs that are going to be isomorphic to each other have to have in common. For instance, they have to have the same number of edges. Also, they have to have the same degree sequence. They have to have the same property with respect to being planar, with respect to being connected. The relationships between the vertices that have certain degrees has to be preserved by the isomorphism if it's going to be valid, and so on and so forth. There's any number of things, and we haven't even covered all of the concepts yet that we can look at. So I just wanted to do a couple examples here, kind of get you in the mood for this and understanding it a little bit. So I put two graphs up here, and the question is to decide whether they're isomorphic or not. So this one's pretty easy. It's just a warm-up problem. You can see that there are 5 vertices, and of course we could count how many edges there are. Usually vertices and edges are what I like to look at first. But what you'll in particular notice about them is that their degree sequences are going to be problematic. So for example, in the first graph here, right, vertex A, C, D, and E all have degree 3, and vertex B has degree 2. So remember that we always list the degree sequence from larger to smaller. Okay, but on the other graph, what we'll see is that the degree sequence, there's a vertex of degree 4, right? And then there are 2 vertices of degree 3 and 2 vertices of degree 2. The sum of the degrees of the vertices is actually the same for both graphs, which means they would have the same number of edges if I actually bothered to count them. But the degree sequences don't match, so therefore these are not isomorphic. These are not isomorphic graphs. Okay. I mean, another way to think about it is, if you do have an isomorphism, theta, between G and G prime, if I have two graphs, G and G prime, then if you take a vertex V and you map it, so this is little v, and you map it to theta of little v, one thing to keep in mind is that the degree of this vertex, theta of G, will have to be the same as the degree of V. In other words, theta is going to respect the degree of the vertices. So clearly we're going to have a problem because this vertex that has degree 4 right here, vertex 2, isn't going to be associated through this function theta to a vertex of degree 4. So, but this is a helpful thing, like if you have a graph and there's exactly one vertex in each graph that has degree 4, then you know that the theta would have to map those vertices to one another. Okay, but here we don't even have that. We have a vertex of degree 4 on one side, but not on the other side. So these graphs are not going to be isomorphic at all. Okay, hopefully that makes some sense. Okay, what I'm going to do next is take you over to a harder example. And I've put that one up here on the right side of the board. This is actually going to look familiar, pretty familiar to you, because I used this example in class. I kind of worked my way to it at the end of class on Wednesday. And so I've just reproduced the figures here. Notice that both of these graphs have order 8. And every vertex on both graphs has degree 3. Okay? So in terms of degree sequence, in terms of number of edges, number of vertices, they're obviously both connected, and so on and so on. So some of the easy things that we would use to test graphs for isomorphism seem to be holding up. So what we can try to do in that case is we can try to create a bijection and see if we can make it work. So for example, what I'm going to do is I'm going to just kind of arbitrarily decide that my function theta is going to map A to 1. Now, I don't have to do that. There's not necessarily just one unique isomorphism. But I'm going to give it a shot, so to speak, of associating A to 1. Now, here's the next thing to realize. The 3 vertices that are connected to vertex A are F, G, and H. You can see that the way the edges are. So what I'm going to do next is actually try to figure out what happens with F, G, and H. Now, if I come over to vertex, so let me just put little diamonds around those vertices, actually. Okay. If I go over to the other side, the second graph, I also have 3 vertices that are connected to vertex 1. So what I should expect here is that F, G, and H have to be mapping somehow to 2, 5, and 4. In other words, these 3 vertices that are connected to vertex A have to be in some way associated through theta to these 3 vertices, 2, 5, and 4, that are connected to vertex 1, so that we're preserving the edges, right? So we're trying to preserve the edges that A is connected to and make sure that they map to the edges that 1 is connected to. Okay, so, you know, in some sense, this is a little bit of a random choice. What I'm going to do here is I'm going to map, I'm just going to map these to 2, 4, and 5. I'm just going to try that. In other words, these 3 numbers, 2, 4, and 5, I'm going to associate with F, G, and H. Okay. Now, that's still only half of the graph. By the way, you'll notice that in the first graph, F, G, and H have no edges between them. But the same thing is true for 2, 5, and 4. There's no edge between 4, 5, or 2 in any way. So we are preserving non-edges. The non-edges between F, G, and H are still going to be non-edges between 2, 4, and 5. So far, so good? So we have 4 other letters to look at, which are B, C, D, and E. Okay, now here's something that's kind of a neat way to think about this. Look at vertex B with me real quick. Do you see that vertex B is connected to both H and G? And so is vertex A, of course. Those are the only 2 vertices that are connected to both H and G. So notice C is not connected to G, and D is not connected to H, and these are not connected to either G or H. The only vertices that are adjacent is really the word I should be using here. The only vertex that is adjacent to both G and H, other than A, is vertex B. So let's look on the other side of the function. G and H maps to 4 and 5. What is the only vertex that is connected or adjacent to both 4 and 5 other than vertex 1? The answer is vertex 8. So therefore B right here, this guy, has to be associated now to vertex 8. So we made some arbitrary choices in the beginning, but now this one is forced. 8 is the only place that we can map vertex B, because 8 is the only one that is connected to both 4 and 5, while B was connected to G and H. And you see G and H are associated to 4 and 5. Again, this was an arbitrary choice. If we didn't do 2, 4, 5, if we did like 4, 5, 2 here, well, then that would jumble up what we're defining on the other side of the equation as well. Okay, let's see if we can use that reasoning on another vertex. Let's look at vertex C. Now, if you look at vertex C, well, you can see that it is adjacent to both F and H. right? F and H. So I want to look at F and H. That's 2 and 5. So where are vertex 2 and 5? They're right here. So I can ask the same question. What vertex on this graph is adjacent to both 2 and 5 other than vertex 1? The answer is just right here. It's 6, right? So that means that C, right, just put a big square here, C has to line up with 6, okay? Now we're almost done. Okay, let's look at one more. Let's look at vertex D. D is adjacent to both F and G, but not H. So F and G is 2 and 4. So is there a vertex that's adjacent to 2 and 4, but not 5? So 2 and 4 is here. I'm looking for a vertex that's adjacent to 2 and 4, but not adjacent to 5. It's right here, 3. So that means D is going to go to 3. And then the last one, there's only one letter left, which is E has to go to 7. And let's just make sure that seems reasonable. So E going to 7, E is adjacent to which vertices? E is adjacent to B, C, and D. So and where did B, C, and D go? They went to 3, 6, and 8. So is vertex 7 adjacent to 3, 6, and 8? Absolutely is. Okay. So this is a valid isomorphism, right? It took a little bit of work. It was a little bit arbitrary in nature. It's not the only isomorphism, but when you're constructing an isomorphism, this is the kind of analysis you need to do. And I'm okay with you just giving me this. There's not a lot of work to show here. I can't write down a whole bunch of calculations necessarily. But obviously, it's easy enough to check if it's correct or not by just looking at edges and non-edges. So that's just a quick little brief example of graph isomorphism. Oh, let me give you one more trick. I'm going to give you one more trick. Let's go back to the first example again real quick. I didn't tell you about this before. This is another way to tell if two graphs are isomorphic, which is to, let me draw this first picture again one more time. If you take a look, and I'm going to draw this one too. Sorry, I'm getting ahead of myself. If you take the complementary graphs means I'm going to erase all of the edges that are here, and I'm going to put in the edges that are not currently here. So for example, vertex A is not connected to vertex E, but it is connected to the other three. Vertex D is connected to everything except B, so in the complementary graph I'm going to connect those together. And C is also not connected to B. And I think that's it. These blue lines are actually the edges that are missing from this figure. Now let's look at the complementary graph of this one. So I'm going to put in the non-edges. So there's no edge from 1 to 3. There's no edge from 1 to 4. There's no edge from 3 to 5. What else? That might be about it. Does that look right? Yeah. So these two graphs, turns out, here's a quick little idea. Because remember, isomorphisms preserve edges and non-edges. So if I take out the edges and I look at the corresponding graph of non-edges, I can ask, well, are those the same? Well, look what you have. This graph right here is really just 3 line segments. 1, 2, 3. This graph over here is like 2 disconnected line segments. So they're not the same. The reason you would use that trick is that if there's so many edges up here that you have a hard time analyzing it, what you can do is you can say, well, let's look at the non-edges instead. Now that doesn't help us so much. That trick doesn't help us so much over here, because if you replace the edges of these graphs are already pretty messy. If you replace the edges with non-edges in this picture, you're going to have even more edges. It's going to be an even messier graph. So I don't necessarily recommend it on this example. It works, that trick of replacing edges with non-edges tends to work really well if your original graphs have lots of edges in the first place, because you can remove those edges and look at a graph of the non-edges instead. So, okay, that is my mini lesson for the weekend. I'm going to let you guys start thinking about isomorphisms and doing some homework problems. And be sure to stop by and ask me for help if you're having any trouble with any of this. All right, so thank you very much.